Okay. I'll share my screen. So let's see. All right, today it's probably going to be a little bit late since there were some issues with technology. So you probably just hang on tight. And okay, today our topic is about measurement and uncertainty propagation, which is basically measuring how like certain or precise like your value is. Because first of all, unlike math, physics is a science. So science is all about measurement to find trends. Now, measurement does not have to be completely accurate, and oftentimes it is not completely accurate. So it's very important to understand how the possible inaccuracies or discrepancies in your measurements can impact like things that you would ultimately derive from your answers. So let's say if you're measuring time, if you're trying to find velocity or distance, that can be impacted by like any variations in your time measurement. So each measurement can impact like the derivation of another one. So it's important to understand why this is the case and how do we deal with this. So like we said before, it is basically inevitable that experiments will vary from what you think theoretically. Sorry. This is because obviously our measuring, we're not computers, and even then computers cannot measure everything exactly to like the precise value. It can only go to a certain number of digits. So the accuracy and the precision of a measurement is always limited by the degree of refinement of the apparatus used. So it can also vary based on how experienced you are with the equipment and by the basic mechanics or phenomena that actually occur in the experiment. So there's three main types of uncertainty. The first one is instrumental limitations, which is limitations set by how accurate your measuring device is. So a lot of people have rulers in their houses. So you can see this. This is a simple ruler that goes down by inch. So you see where these two fingers are. This is a 1 inch difference. And it's divided into halves. So this would be the point in the middle, 7.5, and then this is further divided into 7.75, 7.25, and then there's a smaller line that goes here that goes to values such as 7.125, 7.375, and so on. And it eventually goes down to the 16ths, so 1/16th of an inch. So we know that this measurement is precise by 1/16th of an inch. But let's say, for example, if the length of our object was between like 7 and 1/16 and 7 and 1/8, if it was somewhere in between there, we wouldn't be able to guess like exactly how far it is from like our marker at 7 and 1/16. We can only estimate. Systematic errors are caused by factors that do not really change during the measurement. So they're not random, so they can never really cancel out. They do affect the accuracy, but again, they do not affect precision. Now, normally accuracy and precision are used as like interchangeable terms, but in science, they are not the same. So accuracy is correctness, which is how close a value is to its theoretical or like true value. And precision is how close they are, and also the amount of significant figures. So it's precise to what degree. Precision between multiple objects is basically how close they are in terms of numerical value. So you can be accurate, but you don't have to be precise. And you can be precise while being inaccurate. And then the third type of uncertainty is basically random errors. They arise from unnoticed variations in procedures that you did in the experiment, such as measurement technique, tiny changes in the environment. And these also, you can't really like prevent these, as like, for example, environments are always different. So things like pressure and stuff will always change depending on your location. It's just that it usually isn't big enough to impact it on a large scale, but it doesn't mean it's not there. The most common way in physics and most of science to show a range of values and the uncertainty is basically this formula. So you have this measurement. So let's say you say mass equals to what's your best estimate. So this is always a number and then followed by the SI units. So 7.05 kilograms, for example, then plus minus the uncertainty. So you say mass equals 7.05 kilograms plus minus 0.01 kilograms. And then you can get rid of the kilogram in front of the first number. So you say mass equals to 7.05 plus minus 0.01 kilograms. So what we are going to go into pretty deeply today is measurement uncertainty. So measurements are quantified by associating them with an uncertainty. That's your measurement uncertainty. So for example, you first of all have absolute uncertainty as a way to express measurement, and it was also the way that we discussed earlier. So you express exactly what your uncertainty is, and you also express what your best estimate in terms of how many digits does it go down and how close is it to your answer. You express your best estimate plus minus your uncertainty. So you just say this is length is plus minus 2.59 plus length equals to 2.59 plus minus 0.02 centimeters. Percentage uncertainty would show what it's basically your error, but as a percent. So you say like 7.7 centimeters plus minus 1%. So we know that this 7.7 centimeters, the true value should be about at most 1% away from this true value. How do we know which digits to include and which digits to not include? Here we would use the principle of significant figures. Significant figures are digits like in a measurement that actually have influence and physical meaning. So there are rules in defining what is a significant figure and what is not a significant figure. So all like digits that are not a zero are considered as significant. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Leading zeros though in a decimal. So if you say if you say like 0.01, these two zeros are not significant because they're considered as leading zeros. One way to think about this, how to express your number in scientific notation. So here you would say 0.00231 meters is equal to 2.31 times 10 to the power of negative 2 meters. Now notice that there's obviously only 3 significant figures here, the 2, 3, and the 1. So we can thus say that these 2 zeros in front are not significant. You can also just convert it into like something that only has that just doesn't have leading zeros. Okay. Trailing zeros, however, that means zeros at the end of numbers that are not zero in a decimal are actually significant figures because they do indicate how precise the number, like those definite digits, the digits that are not zero, it does indicate how precise it is. So I'm just gonna come up with some examples, and if you want, you can put your answers into the chat. This shouldn't be too difficult. I think some of you guys should already be familiar with how this works. So let's say we have this number 1,200. So put into the chat like how many significant figures does this number have? Well, okay. The answer is 2 because first of all, let's just do it by looking at each digit. 1 is significant, right? 2 is also significant because they're not 0. So the last question remains on whether these two can be considered as significant. They are not, though. So again, you can think about it as expressing it in scientific notation. These zeros, again, this is considered as a leading 0. These do not really indicate precision. So when you write it in scientific notation, you still write it as 1.2 times 10 to the power of 3, where you would immediately tell this is just 1.2. So yeah, so there should be only 2. Okay, our next example is 0.107. Now, here, although there's a 0 between like the 1 and the 7, this 0 is actually between the 1 and the 7, which are non-zero digits, right? So yeah, there's 3 significant digits here. This first 0 does not count. This is a leading 0. 1 and 7 count, and this 0 in between also counts because it's not a leading 0. And it does indicate precision, how precise this is 1 and 7, whereas in like the number is the 1 and the 7. So yes, 3 significant digits here. Our next example is 1.5301000. Yes, there are 7 significant digits here. Every single number here is actually a significant figure. So obviously you have all these like you have all these non-zero digits that obviously count. This 0 is actually between 2 non-zero digits, so this also counts as well. These 2 zeros are trailing zeros and are used to indicate like how precise like this 1 is at the end. So yes, they count as well. So all 7 digits are significant. So I think we have a bit of a hang of how this system works. So we're gonna talk about why this is important. Oh wait, I forgot to mention at the end, one last note is that in uncertainty, it should always be 1 significant digit because when you're reporting measurements, it's always that last digit that's the uncertain digit. So if you have centimeters and it's between like 2.41 and 2.42 on the ruler, and you estimate it as 2.415, it's only the 5 that is an uncertain digit. So your significant, so when you're expressing uncertainty, your uncertainty should only be that digit in the thousands place, nothing else. Everything before that is already fixed, and everything like to the right of that is small enough that it's basically negligible. It's that main part, that thousands digit in that example, that should be reported as your uncertainty. So it should only be 1 significant digit, and it should be that final one. in like, it should be like in the same decimal place as the final digit of like your measurement. So we will see this become important later when we're manipulating with what uncertainty is. Significant digits are also used in addition, subtraction, multiplication, division of numbers in science. It works a bit differently in math. In addition and subtraction, the number of digits you round your sum to is actually equal to what you have to look at, like the decimal place of the two numbers. The decimal place that is to the leftmost decimal place. So if you have like 3.65 plus 3.5, the leftmost decimal point of the leftmost decimal place of the two numbers is the 3.5. It's only 1/10, while the 5 and 3.65 is 1/100th. So you would round to the tenths. In multiplication and division, however, you round to the number with the least number of significant digits. So that means if a number has 3 significant digits and it's being multiplied with a number that only has 2 significant digits, your final answer, your rounded answer for that product should only have 2 significant digits. So this is where it becomes very important, and we will discuss here how does rounding work in science. So rule 1 and rule 2 is basically been ingrained into your mind since like 2nd grade in elementary school. You have like, if that final digit is less than 5, you just drop it, you round down. So 5.3 will round down to 5. If that last digit is greater than 5, you round up to the next number. 5.6 rounds up to 6. However, if the remainder is exactly 5, things change. Normally in math, you just round up, but this can't really be like that in science, because that'll create a rounding bias. Every number that has 5 as the final digit will have to be rounded up, and then your numbers will be a bit inflated. So if you're given a large data set, the numbers with remainders of 5, or numbers whose last digits are 5, are rounded down half the time and rounded up the other half the time, depending on what even number is closest to it. So we have this example here. Here we have the number of 3.55. This is rounded up to 3.6, but 3.65 rounds down to 3.6. Now this seems very confusing, but how I treat this kind of thing is that I would actually move this decimal place until we only have that 5 digit left, however many times it has to go. So if we say 3.55, it is now 35.5. Now, at this point, you disregard the 5 and you look at this number on the left, and you ask yourself, what even number is that closest to? Here, 35.5 is closer to 36 and 34. We know 35 is between 34 and 36, and since it's here, we actually have this additional like component, this additional like portion. We would say, well, this is closer to 36, so this will become 3.6. Likewise, if you do the same for 3.65, you get 36.5. Now, 36.5 is between the numbers 36 and 38. So I would say, which one is it closer to? 36.5 is obviously closer to 36 than it is to 38, so you would round down. Again, this seems kind of confusing, but if you guys just have problems with it, I'll just correct you. And here it is mostly practice, which makes perfect. So having experience and like trying these out with like a few numbers, like for example, multiplying simple numbers and then rounding to the correct numbers of sig figs, that can help in this kind of scenario to get you familiar with this. So here's a little bit of a example like flurry for us. So are you able to identify why each case should be corrected as so? So for example, why is this wrong? If you know the reason why this first example is wrong, you can put it into the chat box below. No, not really. Correct. 3 point here, you look at the uncertainty digit. You see, the last digit in your estimated measurement is the hundredth place. So there shouldn't be a thousandth place in your uncertainty measurement. It should only go down to a hundredth. Furthermore, this has 2 sig figs, which is wrong. Uncertainty measurements must only have 1 sig fig at a time. The only exception to this is if the uncertainty measurement is big enough so that it has like a 5 as its residual digits, in which case you'd include a 5. But in most cases, since it's often not 5 as the last digit, as like a last digit, you can only include 1 sig fig, and it has to be at the same place as your final uncertain digit in your measurement. Okay. Example 2. Why is this wrong? Yeah, here it is actually the measurement here of the estimate. This 3 should not be here because remember, your uncertain digit is in the hundredth place. That means that starting from the hundredth place here, we are uncertain whether this 9 is the actual is actually correct. This is just like so this 3 is even more uncertain, and it should not even be included in the first place. So there's our general rule that that one significant digit in that the uncertainty measurement, the absolute uncertainty measurement that you put into your answer expression must be in the same decimal place as your final digit, the one that's supposed to be uncertain in your estimate. So here 3 is in the thousands and this 3 is in the hundreds. So this 3 in the thousands should not be included. Your uncertain digit should be in the hundreds. And the third example, what's wrong with this? I mean, our velocity was found to be about 2.45 meters per second, but our uncertainty is already in the 10th digit. Correct. It's rounded wrong. So this is how you would round in math. If you're taking a math class, this is how you're supposed to round it. But this is not how it works in physics. Remember how we were talking about this in the last slide, that when you round, you actually look at your closest even number. So here, when you do this, there will be 25. And then which one is it closer to? You get 24.5 by moving this to the final 5 place. So which one is this closer to? 24 or 26, which are the closest two even numbers? Well, it's obviously 24. So you would say this would be 2.4. Yeah, we kind of discussed this in the last slide, but you have to look at like this side here. You have to look at this left side. This has to be an even. This like left side has to be even. That was the rule for rounding with a that was the rule for rounding with a remainder of 5, because otherwise it would be too vague. no one knows how exactly accurate that answer is. So you look at the closest even place in the digit before the 5. So here it would be that tens place. Yeah. So for example, if you have let's say you have 2.4, right? If you, let's say, because this is considered as technically even, if you multiply this by 10, that would be 24, which is an even number. And you have 2.6. Now, between these two intervals, there are two uncertain, there are two the vague rounding numbers. You will have 2.45, right? And you have 2.55. We don't include 2.5 here because that'll be the same thing as saying 2.50, which is already considered as even on its own. You're trying to round to the tens. So you have these two uneven numbers, and you have to find out how do you round this so that you won't create a rounding bias. So you would say, well, this one just rounds down because it's closer to 2.4, and this one will round up because it's closer to 2.6. That way, you won't get an inflated rounded number, and this is basically distributed half of the time. One goes here, one goes down, one goes up. Do you understand? Okay, good. How do I clear this? Okay. Okay, so we're going to start manipulating with the data. So how do we look at this? How do we look at how do we measure what's our best estimate, and what is the uncertainty? So when we look for a best estimate between a data set, not just an individual piece of data, but a collection of data that if you take several runs in an experiment trying to measure time, what type of number should you report as your best estimate of the real time? Well, normally in physics you would report the mean. Here we mean the arithmetic mean, which is basically summing all of the number in the runs, summing all of your run values divided by the number of runs that you took. So you could write it with this formula, and that would be normally how you would report your data. For range, this can tell you how much your data varies. I'm pretty sure most people here know what range is, but for those who don't, range is the maximum value in your data set minus the minimum value, which kind of tells you how far, if in a graph, how far does your data spread out. Uncertainty is a single measurement of one data point. So, no, sorry, it would be the uncertainty in a set. So it'd be uncertainty in one set. So you would look at your range and you divide it by 2, and that would be your uncertainty in your measurements. Well, when I was thinking about an individual thing, I was looking at the next one, uncertainty in the means. Sorry. You would calculate this by looking at your range and then divide by 2 times the square root of the number of measurements you took. So your mean value obviously will almost never be the true value of what your actual value is. So this will give your neighborhood range of where this true value will fall in relation to the mean. Okay. Here, this is how, again, this final one is just repeating how we normally report measured values. Your measured value should be that best estimate, which is that here it's the mean, plus minus your uncertainty. Here it's uncertainty in the mean. This is how you report your data in a lab. Okay. So let's look at this example. In an experiment, a car was dropped down a 1 meter long ramp when we were measuring along the surface, not horizontally, and we were taking the time. So we've recorded 4 times in 4 separate runs. So you'll have 4.23 seconds, 4.29 seconds, 4.19 seconds, and 4.27 seconds. So how do we report what is most likely the time that took for the car to roll down the ramp? Well, our best estimate value, if you remember the last slide, is taking the mean of these values. So that would be 4.25. To see our uncertainty, we would remember that we would take our range and divide it by 2. That would find out what the uncertainty in the set is. So we see that 4.19 is the smallest and 4.29 is the largest. So this range should be 4.29 minus 4.19, which is 0.1, divided by 2, that's 0.05. Now the mean of the average would be that divided by the square root of your the number of runs that you took, which is 4 here. So you have your uncertainty that you figured out last time divided by 2 here, which is from the square root of 4. So you get approximately 0.025, but remember here we have the round down. So you'll say 0.02. So thus you would report your uncertainty would be 4.25 plus your measured value would be 4.25 plus minus 0.02 seconds. So this is how it will work. Does anyone have any questions? No? Okay. If you have a question, feel free to just speak up. I'm using the microphone. So, because I can't really see the text box right now, it seems to not load. So if you have a question, just please unmute and speak it up. I don't really care if you interrupt me, just speak out your question. It's always better to ask. Okay, well, for large data sets, okay, so the measurement of the way to report your best estimate again in a set, it's still the mean. That can include like if you really had a possible outlier that can actually impact your best value. So you would actually have to use the mean here. Again, the x-average formula is the exact same as for small. It's just that you're probably gonna have to do more math since you're adding up more numbers. Uncertainty, however, has changed. It's now your standard deviation. Standard deviation is to measure how approximately, like on average, or like how much an expected values will be expected to deviate from your mean. And how we will get this is we will first find the variance, which is adding up the squares of the differences between each of the terms and your calculated mean. So you would take for each one, find the difference between each value and the mean. You would square those so that can get rid of the negatives, and you would add them all up together. After that, you would divide by the number of runs that you took, and then you take the square root of that because you were previously squaring it. Uncertainty in the mean is now your standard deviation divided by the square root of n. So it's basically the same formula as last time, except now instead of the uncertainty in the measurement being r over 2, it's now sigma, which is your standard deviation. Okay. Anyway, the measured value is exact same. You have to report all your measured values like these. So this one didn't change at all. Okay. If we are looking at this from and we're analyzing this from the perspective of assuming that this is a large data set, even though it's not really. we would actually get the same answer. So obviously our x-average did not really change. But here there's a slight difference, although it's very insignificant. Here your uncertainty would be your standard deviation. So how we would find this is that our mean is 4.25 and we have our 4 terms each here. So by we have to find what the difference each how far away each of our 4 values are from our mean. So 4.23 is obviously 0.02. 4.29 is 0.04. 4.19 is 0.06. And then 4.27 is 0.02. So you square all these values, add them together, and you divide by 4, and you get 0.016. And then you take the square root, and you get 0.04. That is your standard deviation. So here, your uncertainty in the measured set is a bit lower, as is usually characteristic of larger sets. And however, our deviation in the mean is a bit smaller than what we measured last time, but it's still it's pretty much the same because we rounded down from last time. So instead of 0.025, it's pretty much exactly 0.02. So thus our answer is, we will express our answer as 4.25 plus minus 0.02. How did I get 4? 4 as in you mean like this 4? Oh, 4 is the number of runs that you took. So here we recorded 4 values. So you divide by 4, just like how in the mean, you divide by 4 values here. You do the same in standard deviation. Okay, no problem. Okay, here we're going to get into stuff that's a little bit more complicated and a little bit more conceptual. So we just discovered what uncertainty is. Other words for uncertainty are things that you've probably heard before, such as error and deviation. It's more common to call percent uncertainty as a percent error. It's very common to hear that. And that's often used to try to express in labs how accurate or consistent your answers are with an actual theoretical answer. But here, when we mean error, we have 3 different types. We have absolute error, which is our uncertainty value. We have a relative error. That means how, so that's basically fractional uncertainty. How we would find that is that we will take our absolute uncertainty and we will divide by the number itself. So relative to the number that you're doing it yourself, the relative to your measured value, what is your fraction? What is how significant is your error? Percentage error here is your fractional uncertainty. That's uncertainty divided by the actual measure number multiplied by 100%. So yeah, it's just a different way of expressing relative error. Propagation of uncertainty in calculation in science is a huge topic, and it can get extremely difficult, like to the point that it needs to be able to fully understand it. You need complicated math and a very, very good knowledge of how the measurement system works and how like time works actually. So to be able to actually easily understand it so that we don't always make things wrong, we would use a simplified propagation. So this is where a beginner will start, and it's typically taught in class how you would manipulate uncertainty. Another way to do it is standard deviation. So you look at the standard deviation, then you would determine how much your uncertainty is. It's not very difficult compared to simplified, but the results are quite close. So these two are generally like what you will learn in like if you don't want to measure and you're just taking it taking like physics or some type of science as a one-off class, you would learn these because you don't really need to go in depth, because going in depth is extremely confusing and complicated. So we're not going to really discuss this, and for the rest of the slide, we'll discuss these top two. Simplified uncertainty propagation is just properties that we can use to find uncertainty given other values of uncertainty and the relationships between what type of measured values you have. So let's say we have delta x as the uncertainty for x, delta y is the uncertainty for y, and delta z is the uncertainty for z, which x, y, and z are all measured values. So we would have, if you calculate the measured value of z as x plus y, your uncertainty for z should be the sum of x and y. It should be the sum, for clarification, sum of the uncertainties for x and y. So that means that addition carries over. In subtraction, if your value z is the difference of x and y, your uncertainty in the z, it's still the sum of the uncertainties in x and y, because you can't really take out uncertainty. You only can add on more uncertainty. So you would express it like so. Multiplication of z is equal to x multiplied by y. We know that the relative uncertainties, that means that the uncertainty divided by the actual measured value. So here it's delta z over z is equal to the sum of the relative uncertainties for x and y. So delta z over z is equal to delta x over x plus delta y over y. The same applies for division. So z would be equal to, if z is x over y, delta z over z is equal to delta x over x plus delta y over y. It carries over as well. For powers, if z is equal to x to the power of n, then delta z over z is that exponent times delta x over x. And if z is a constant times x, delta z would be the absolute value of that constant times delta x. Another way we can express this is with standard deviation, like these formulas. So again, we have our delta x, delta y, and delta z representing our uncertainties for x, y, and z. So this time, if we're looking at it from the view of standard deviation, if z is equal to x plus y or x minus y, if it's the sum or difference, our uncertainty in z would be actually the square root of the square of the uncertainty in x plus the square of this uncertainty in y. Here in multiplication of z equals to xy, delta z is equal to absolute value of xy times the square root of the sum of the relative uncertainties of x and y. In division, this square root of the sum of the squares of the relative uncertainties remains the same. This entire right-hand side remains the same. The only real difference is that when we're looking at our values of x and y, obviously it can't be multiplied. We're not looking at z is not equal to x times y, so you just simply replace that with x over y because it's a quotient. Here, if z is equal to x to the power of n, your uncertainty in z would be the absolute value of n, the exponent times x to the power of n minus 1, then times the uncertainty in x. Now, this kind of looks familiar because this is actually the power rule in calculus, except the power rule doesn't have the absolute value signs, but that's like taking the derivative of x to the power of n. However, it does not apply here when we're multiplying by a constant. If z is equal to cx, it's the exact same as with the simplification approach. We'll not go into functions because a lot of the stuff that we try to measure are typically around here and can be just manipulated by adding or subtracting and dividing into pieces. But if we have a complicated function, if z is equal to f of xy, this is how we find it. Note here that df over dy, this is the derivative of like each of the respective values. So of like x and y. So if we have z equals fx plus fy, so we would have like z equals x squared plus y squared. This df over dx would be like the whatever the derivative of x squared is, then times delta x squared, and then this will be the derivative of that y squared. Okay. We only have 5 minutes, so we're just going to go through some of these examples very quickly. So we're going to go through this example. This is actually an f equals this is actually like these kind of problems that you would see in an f equals ma things. Occasionally f equals ma will throw in problems relating to uncertainty. So let's say we have w is equal to 4.52 plus minus 0.02. That's, and then x is equal to this and y is equal to this. Now we have another variable z that's equal to x plus y minus w. How do we find what z is and what is its uncertainty? So z, calculating the estimate value of z is the exact same. You just look at the left-hand side, since these are all the best estimates of w, x, and y, and you directly substitute it into this. So you get z equals x plus y minus w, which is equal to 2 plus 3 minus 4.5. This would equal to 0.5 centimeters. Now, delta z, since we could just break this into apart, this you can combine like this as x plus y and then minus w. So you would have like your uncertainty of x and y, which is delta x plus delta y from the addition rule and simplified. In the simplified approach, plus remember, the uncertainty in w, which is also from the simplified approach. So you would add up each of these right-hand sides. Thus, you get 0.82. Now, note that this is a hundredths place, and the uncertain digit here is the tenths place. It's in the tenths place. So this 2 has to be disregarded. So you round down to 0.8 centimeters. Thus, we would express our answer here as 0.5 plus minus 0.8 centimeters. Is that clear? Okay. Now, if we have w equals to 4.52 plus minus 0.2, and x is equal to 2.0 plus minus 0.2, if z is equal to wx, how do we find it? How do we find the actual value of z and its uncertainty? Well, you can do the exact same thing as last time. You would just say z is equal to w times x, right? That's equal to 4.2 times 2.0. Now, if you just plug that into a calculator, you get that your answer would be 9.04. Okay. Now we have to calculate the uncertainty value. So we would use the multiplication rule here, which would say that delta z over z is equal to delta w over w plus delta x over x. So you just move the z over, so you have your sum of the relative frequencies of w and x times d itself. So we know what each of these values are, because that's just, these delta values are just your right-hand side. You can plug it in. We knew z is equal to 9.4. That was what we got from last time. So if you plug it in and look it up on the calculator and round, you get 0.9 centimeters squared as your uncertainty value. Now, our measurement value is 9.04, and our uncertainty is 0.9. This 4, which is in the hundredths place, should be disregarded because the uncertainty goes down to the tenths. Thus, we would express it as z. We would express z as 9.0 plus minus 0.9 centimeters squared. Is that clear? Okay, so we're gonna go on. This is an F equals MA question from 2019. So you would say so the question is asking, to test the speed of a model car, you time the car with a stopwatch as it travels a distance of 100 meters. You record a time of 5 seconds and your measurement has an uncertainty of 0.2 seconds. What is the uncertainty and the estimate of your car's speed? assume that the car travels at a constant speed and that the distance of 100 meters is known extremely precisely. So that means that the uncertainty can almost be disregarded. I'll give you guys a minute, since we don't really have much time, but if you can solve the answer quickly, you can put the answer in the chat if you want, or you can just go along as I explain this problem. So how we would do it is that, remember that velocity is equal to displacement over time. So let's say it's at L over T. Our uncertainty would follow this formula then. We would use the division rule in terms of uncertainty. Our uncertainty would be then delta V over V is equal to delta L over L plus delta T over T. So you move the V over again, just like we did for Z in the last problem. Delta L is equal to 0 because there's pretty much no uncertainty in what the displacement is. So all we have to do is to find what the uncertainty in the time is. So again, we can distribute it. L is equal to 100 meters, T is equal to 5 seconds, and dt is equal to 0.2 seconds. So thus, when we substitute our values in, we get delta V is equal to 100 over 25 times 0.2. So if you this would be 4, this would be 0.2. So if you find the value, it will be 0.8 meters per second. We don't have enough time to go over another example, so we're just going to skip over this. So does anyone have any other questions or comments? Okay, if not, I will see you next week in the next physics meeting. Goodbye.